The skyline of the South Texas coast was forever altered by the presence of a steel titan, a 400-foot-tall monument to human ambition known as Starship. For years, the world watched as prototypes rose and fell, sometimes in spectacular balls of fire, as SpaceX iterated toward a goal that many in the traditional aerospace industry deemed impossible. This wasn't just about building a bigger rocket, it was about reimagining the very nature of space travel. The traditional model of expendable rocketry, throwing away hundreds of millions of dollars in hardware with every launch, was the primary barrier to the stars. Elon Musk and his team at SpaceX realized that to make life multi-planetary, the rocket had to be as reusable as an airplane. On this historic day, the focus wasn't just on the ascent, but on a maneuver so daring it sounded like science fiction, catching a falling skyscraper with a pair of giant mechanical arms. The atmosphere at Starbase was electric, a mixture of calculated confidence and the raw tension that precedes a world-changing event.
To understand the significance of the catch, one must understand the brutal tyranny of the rocket equation. Every kilogram of weight added to the rocket structure is a kilogram less of payload that can be delivered to orbit. For the Super Heavy booster, the traditional landing legs used on the Falcon 9 would have been massive, adding dozens of tons of dead weight. By removing the legs entirely, SpaceX shifted the mechanical burden from the vehicle to the ground infrastructure. This Mechazilla tower, equipped with its chopstick arms, represents a paradigm shift in engineering. It allows the booster to return to the pad with higher mass efficiency, preserving more fuel for the landing burn, and increasing the overall capacity of the Starship system. This design philosophy, that the best part is no part, is what drove the development of the catch mechanism. It was a high-stakes gamble. If the catch failed, the entire launch tower, the most expensive and complex piece of infrastructure at Starbase, could be destroyed in a single catastrophic impact.
At T-0, the silence of the Texas wetlands was shattered by the roar of 33 Raptor engines. Producing over 17 million pounds of thrust, the Super Heavy booster is the most powerful rocket ever to take flight, nearly doubling the power of the legendary Saturn V. As the vehicle cleared the tower, the sheer scale of the engineering became apparent. Those 33 engines, fueled by subcooled liquid methane and liquid oxygen, represent the pinnacle of staged combustion technology. They are designed not just for raw power, but for the precision required for the return journey. Unlike the Apollo-era engines, these Raptors are built for rapid restart and deep throttling, capabilities that would be tested to their absolute limit just minutes later. As the stack accelerated through max Q, the point of maximum aerodynamic pressure, the world held its breath. The mission was moving flawlessly, but the true challenge, the unprecedented return of the booster, was still ahead of us in the cold vacuum of the upper atmosphere.
Minutes into the flight, the mission reached the critical phase of stage separation. SpaceX utilized a hot staging technique, where the Starship upper stage ignites its engines while still physically connected to the booster. This maneuver, while technically complex, minimizes the loss of velocity during separation, further optimizing the rocket's performance. As the upper stage peeled away to continue its journey toward orbit, the Super Heavy booster performed a choreographed flip. This was the moment the mission transitioned from a standard launch to a high-stakes recovery operation. The booster reignited a subset of its Raptor engines for the boost-back burn, a precise firing designed to cancel its forward momentum and set a trajectory directly back toward the launch site. From the ground, it appeared as a distant star returning to Earth, but on the telemetry screens, it was a complex dance of physics guided by advanced flight control software that had to account for changing atmospheric density and wind speeds in real time.
The descent of a Super Heavy booster is a masterclass in controlled falling. As the vehicle plunged back through the atmosphere at supersonic speeds, 4 massive stainless steel grid fins acted as the booster's primary control surfaces. These fins are not just for stability. They are the steering wheels of the rocket, performing thousands of micro-adjustments per second to guide the 232-foot-tall cylinder toward a specific coordinate in space. The friction of the air generated intense heat, turning the grid fins into glowing embers against the dark sky. This phase of the flight is incredibly violent, with the booster experiencing massive structural loads and turbulence. Yet, the autonomous flight computer remained composed, processing sensor data to ensure the booster stayed within its narrow corridor. The goal was no longer just a soft landing in the ocean. The goal was to hover precisely between two steel arms that were waiting miles below, a target that required centimeter-level accuracy. On the ground, the Mechazilla tower prepared for its guest. The two massive chopstick arms, which had lifted the ship onto the booster just days prior, were now positioned to act as a mechanical catcher's mitt. This structure is a marvel of mechanical engineering, designed to absorb the kinetic energy of a falling rocket and clamp down with enough force to hold it steady, yet enough finesse not to crush the stainless steel hull. The arms are equipped with shock absorbers and alignment pins that interface with specific points on the booster. The engineering team at SpaceX had run thousands of simulations to predict how the tower would react to the booster's exhaust plume and the physical impact of the catch. There was no room for error. If the booster were slightly off course, it could collide with the tower, resulting in a disaster that would set the program back by months. The arms opened wide, waiting for a Titan to fall from the sky. As the booster dropped below the cloud layer, the final landing burn ignited. 3 Raptor engines fired with surgical precision, slowing the vehicle from supersonic speeds to a near hover in a matter of seconds. The sound was deafening, a series of thunderous sonic booms followed by the continuous roar of the engines. This is the death slide maneuver, where the rocket appears to be heading for a crash until the very last moment when the engines gimbal and right the craft. The precision was breathtaking. The booster didn't just approach the tower, it seemed to slide into place as if drawn by a magnet. The flight software was constantly calculating the center of mass and the thrust vector, fighting the chaotic winds and its own massive inertia. The world watched in stunned silence as the 20-story tall rocket hovered momentarily next to the tower, the flames of its engines licking the base of the launch mount. Then it happened. In a blur of motion and steel, the chopstick arms swung inward, clamping on to the booster's designated catch points. The massive vehicle, which just minutes ago was traveling at thousands of miles per hour, was suddenly and securely held in midair. The engine shut down, leaving a momentary silence that was immediately broken by the deafening cheers of the SpaceX team. It was a clean catch. No legs, no landing pad, just a mechanical embrace that signaled the end of the era of expendable boosters. This was the mechanical miracle. The booster hung there, suspended above the Earth, still venting residual gases, looking like something out of a futuristic utopia. In that single moment, the physics of spaceflight had been rewritten. The tower hadn't just caught a rocket, it had caught the future of humanity's expansion into the solar system. The success of the booster catch is more than just a technical achievement. It is a validation of the iterative design process. While others spent decades in the design phase, SpaceX built, tested, and sometimes destroyed hardware to find the limits of what was possible. This catch proves that rapid reusability is not just a dream, but a functional reality. By returning the booster directly to the launch mount, SpaceX can theoretically refuel it and stack a new Starship on top in a matter of hours rather than months. This is the missing link for the Artemis moon missions and the eventual Mars transit. To sustain a colony on another planet, we need a logistics chain that is as reliable and frequent as a shipping port. The Mechazilla catch is the centerpiece of that vision, turning the launch pad into a high-throughput